Okay, welcome to video class 38, and in this video we are going to study about controllers. Okay, so what do you mean by a controller? Okay, controllers are the most important part of a control system. So for that, let me start with the basic block diagram of a feedback or a closed loop control system. Okay, so here is a block diagram for you. This is much familiar for you right now. So, by a control system, we refer to a plant it can be a process which is to be controlled in a plant. So, I'm calling that by a block called as plant. And inside the plant, you have a lot of processes which are to be controlled. And now you have a the output. The output is periodically measured by a sensor, and that will be fed back to, and it will be compared to the reference input. All these things you know, and which will give you eventually give you an error, and that signal is called as an actuating signal, and that's given to a block which is called as a controller. So why it is said to be the most important part of a control system? Because it offers a control signal which is fed to the plant or to the process which we control, and thereby making the necessary control. So we have just so far throughout these modules, module 1 to module 4, we were being dealing dealing with the overall aspects of a control system. Now we are going into the core of that, which seems to be the controller, or which is actually the thing which controls a process. Okay, so this session we'll be dealing more on this block or on this controller. So controller, as the name suggests, it controls or it offers the control signal, and it offers the control signal according to the actuating signal that it receives after the comparison of the reference input and the controlled output, or the feedback signal. Okay, now based on this, the controller can give different types of output. Okay, now this output, this control signal and this actuating signal, when you have an analysis upon the input and output of the controller, there can be some relations, and based on that relationship, controllers can be classified into many ways, and that's what we are going to study. Okay, now let's see what I meant by the relationship between control signal and the actuating signal. Or the control signal is the signal which is offered by the controller based on the actuating signal. Okay, now if the controller output, if the controller output, that is this control signal, if it is proportional to the input, what is that input? Input is the actuating signal or the error signal. If it is proportional to the input, it can be proportional to input. That is a relationship. Or it can be proportional to the derivative of the input. Okay, it is the time derivative of the input. Or it can be proportional to integral of the input, right? Integral of the input. So now some in some cases output can be proportional as well as differential. Proportional to, it can be proportional to differential, integral, and proportional. Now based on that, controllers, so based on the output that it provides, that is the output this controller provides, this output is related to the input in different ways. That is, it can be proportional to the input, or it can be proportional to the derivative of that input, or it can be proportional to the integral of the input, or it can be the combination of all these things, or it can be proportional to input as well as the derivative of the input. So based on this, basically controllers can be classified into proportional controller. Okay, proportional controller, that is this relation. Okay, so corresponding to this relation, now corresponding to this relation, you have differential or differential control or the derivative control. This is called as a derivative control. Okay, now based on this relationship, you can have integral control. Integral control. Okay, so in short, we will call this as uh, P controller. Okay, P, this is D. D stands for derivative, P stands for proportional, and I. Okay, now these are the basic controllers. Basic controllers, and from this basic controllers you can have the combination of this. Okay, now the combinations can be, see, it can be PD controller, meaning proportional derivative controller. It can be PA controller, meaning proportional integral controller, and it can be PID controller, or it can be the combination of these three. So these are the other three combinations of these controllers. So basically controllers are proportional controller, differential controller, and integral controller. Do remember, this classification is based on the relationship between the output of the controller and the input to the controller. Okay, right? Okay, so let's move on to the proportional controller. So this is just a part of a control system which shows the proportional controller. So you have a block which is actually the controller equivalent to this block, and you have an EA of t and EC of t refers to the actuating signal and the controller output. Okay, so I am going to represent here it as in the time domain. So this becomes capital EA of S, and the output will be capital EC of S, where KC is called as K suffix C is called as the gain of the proportional controller. It is the gain of the proportional controller. Okay, controller. So Kc is called as the gain of the proportional controller. So that now from this basic equation, you can say that EA of t into EC of t, if this is a gain, it works as a gain. You can simply say that, write an equation corresponding to EC of t and EA of t as EC of t is equal to K times or Kc times EA of t, right? Or taking the Laplace transform, this will be EC of S is equal to Kc into EA of S, right? Okay, so this is it. This is Kc. Kc is the gain of the proportional controller, and it is in some sense, or in a true sense, you can call this, or you can consider this proportional controller as an amplifier. You can consider this as an amplifier with a adjustable gain, Okay, so this gain can be adjusted so that so as to give the correct control signal to the plant. Okay, so the gain of this controller is adjustable, so at every time it gets adjusted, this equation is there, that is, the output will be always proportional to that particular gain into E of t. Okay, so the proportion in a proportional controller, what it does is easy. Why it is called as proportional controller? Because this controller output is proportional to what? Proportional to the actuating signal. So when you equate, there you need a you need a constant of proportion, so that is Kc, and where Kc is called as a gain of the proportional controller. Okay, now let us study the impact of this proportional controller by considering a case. Okay, to study the effect of proportional controller in a control system. Okay, I have considered a case. You're controlling a process. This is the process, and this K by S into S plus A is actually the transfer function of this particular process. Okay, so it can be a mechanical system or it can be an electrical system which you are controlling. So every electrical, we have already seen in first module that any electrical system or mechanical system can be modeled mathematically by its transfer function. So you can have the process by its represent by its the process by its transfer function. Okay, so this can be represented by a block diagram, and this is the thing which is to be controlled. Okay, now for that we are using a proportional controller. So there must be a block corresponding to Kc. Kc is nothing but it is the gain of the proportional controller, or it is the adjustable gain, as we have studied. So this is an adjustable gain, and what is this input? This is the actuating input, and the okay, this is your actuating input. I am calling this, and everything I am calling it as EA of S. And what is this? This is EC of S, because this is the controlled output. And as usual, this is the controlled output, so I'm calling it as C of S. This is the reference input, so I'm calling it as R of S. And this is the feedback signal, and which we know that your H of S is equal to 1, right? Because it's a unity feedback system, that to a negative feedback system. Now we have one more summer over here. I've shown a summer, and this is actually a case, a particular system. This process is being controlled by this proportional controller. Now, to study the case, we need to induce, we need to, give some disturbances to the system. For giving the disturbance, I'm assuming I've drawn a summer over here. So consider that you have a D of S. Let D of S be the disturbance. So what is D of S? D of S is the disturbance. Okay, so disturbance was not there initially. So during the course of time, some amount of disturbance can come into the system. So D of S is the disturbance that's shown, and the disturbance gets added. So obviously, so if it would not be there, we can assume that this particular system is in control. Now, because of this disturbance, an external disturbance, this causes some problem with the output of the system. So what must be the duty of this proportional controller? The proportional controller, based on the feedback that it receives, it should give a proportional output, so that it should nullify the impact of this D of S on this, because this R of S is given for this controlled output. Now this R of S, so every time this R of S will be combined with the feedback signal, and because of the introduction of this disturbance, the output gets affected. So obviously the error, some amount of actuating signal will be there. Based on that, you will be having an EC of S. Now we are going to analyze this case to study about the effect of the proportional controller. Okay, now we know how to derive the output. I mean, without this D of S, you know how to find out the overall transfer function, and from that you will be able to get C of S by R of S. Okay, now after evaluate, and if you know this R of S, you can very well find out C of S, and taking the inverse, you'll be getting the output response, and you can see that the output will be in the controlled way. Okay, now because of the presence of D of S, we want to find out the impact of D of S. That is, we are concerned with C of S to D of S, right? So D of S can also be treated as one of the inputs as this R of S, right? So now look at this. This system is having two outputs. So how will you find out the effect of C of S, the C of S due to this D of S? Okay, if you have more than two inputs, and not only that, we had an assumption earlier in our module, that is in first module itself, we have already declared that whatever we study is a linear time invariant system. So now, as long as it is a linear system, this will be following the superposition principle. Therefore, you can see that the impact of C of S is due to this R of S as well as D of S. So we are worried about the impact of C of S due to this D of S. Now, how will you find out this? This you can find out by putting R of S to 0, right? This is superposition principle. and you can find out the z of s to d of s. Now you will be getting that as, okay. Now when you consider the impact of d of s only, if you are putting this as to 0, that means you have only one input side over this time. So this is equal to 0. So you don't have to consider the summer. So that means this kc becomes, this minus kc becomes a part of this feedback, right? And that is shown here. Okay. Now minus kc is shown as the feedback. One of the input is d of s, and it is your c of s. Now from this you can calculate what is c of s by d of s, right? What is c of s by d of s? That is the basic expression, g of s, that is k by s into s plus a divided by 1 plus g, it is minus, right? It's a negative feedback. You can call this as 1 by g as hs. So this will be k into kc by s into s plus a. Okay, so you will get this as, okay, get this as k by s into s plus a plus k into kc. What is this k? K is actually the forward path gain of this process. Okay, so I have already told you that the plant will be having a process, and that process can be an electrical system, or it may be an electrical system or a mechanical system. So you can model that as in the Laplace, the transfer function, and that constant, that k, will be the forward path gain of that particular system. So this is the gain, while kc is the controller gain, or the proportional gain, right? Gain of the proportional controller. Okay, hope you understood this. Now, okay, now look at this figure again. Now what you have done is you have made this r of s to 0. So r of s is to 0 means what will be your ea of s? Ea of s will be negative of c of s, right? So from this figure you will get this ea of s as equal to minus c of s, right? Now from this equation you will be able to get what is c of s. C of s is nothing but it is d of s into k by s into s plus a plus k by sc. So from this you will get this as minus k into d of s divided by s into s plus a plus k into k suffix c, right? Okay, now let's see. So let us assume this d of s to be a unit step input. Okay, d of s to be unit step, meaning the input that came over here is an u of t. So what will be this is d of s. D of s means it is a Laplace transfer of u of t. So we know that. So d of s, or let us call that as small letter d of t. Let d of t be u of t. So what will be your d of s? D of s is 1 by s. This is just an assumption. Let the disturbance be in the unit step form, so that it will be 1 by s, right? So you can rewrite this expression as, so this ea of s will be equal to minus k by s into s plus a plus k into kc, the whole into 1 by s. Okay, now what is this ea of s? Ea of s is actually equal, is the output of this controller. Now this output is proportional to what? This error signal. So in a sense this also represents an error signal. Now you can find out the steady state error. Okay, let us have a recollection of what we studied earlier. Say, what do you mean by steady state error? Steady state error is e of t. E of t at t tends to infinity. Now suppose if you have its Laplace transform, how will you get? That is the final value theorem. Applying final value theorem, limit as s tends to 0, you will get the steady state error. Okay, so this is actually the steady state error. So what I'm going to do is, so in order to find out the time, that is the value of this error signal, okay, that is a steady state error. So I'm calling this as a steady state, ASS, meaning AE, that is the actuating signal. Steady state error is actually limit, okay, limit s tending to 0 s into ea of s, right? Or this is limit s tending to 0 s into, okay, this whole thing into 1 by s. Okay, you may write down that by yourself. So this s and s get cancelled, so that you can say limit, then you need to apply limit s tends to 0 minus k by s into s plus a plus k into kc, right? Okay, so when you apply s tends to 0, this becomes 0, right? So this becomes 0, this part becomes 0, and now you don't have any s over here. So when you will be getting this as 1 by kc. Okay, so the steady state error EASS is found out to be 1 by kc. Okay, now what you understood from this? Now you will be getting a conclusion. From this you can conclude. What is the conclusion that you can draw from here? That is, the steady state error decreases for high value of kc. High value of kc. What is this kc? Kc is actually the adjustable control gain of this proportional controller. Okay, so when you add a proportional controller, that is, what's the meaning of a proportional controller? It will be giving a output proportional to the error signal, so based on the controller gain, right? So that is equal to, that is given by kc. Now if you can choose a big high value of kc, what this expression suggests is the steady state error due to the disturbance resulted can be reduced or minimized if you can have high gain. Now the next point is there any problem in increasing the gain to a very high value? Let us see that. Okay, now to study the impact of increasing to a very high value, we need to make this d of s to 0. Okay, d of s to 0, that is, there is no disturbance, and we need to find out the impact due to this r of s, due to the only input r of s. So that you can see that when d of s is 0 in this figure, this is just a straight line, right? So what will be your g of s? G of s will be k into kc by s into s plus s. H of s is 1. This is a simple canonical form. So you will be able to get the transfer function as, so you will be getting the, what is your g of s here? So your g of s will be equal to, what you are going to get is g of s will be equal to k into kc divided by s into s plus a, right? Okay, so this is kc into k divided, so this has got no value because d of s is 0, so that means this summer has no value, so you can take it f and you can just short this. So you are going to get a g of s something like this, k into kc by s into s plus a, which is actually so therefore g of s into h of s, which is equal to 1. So this is actually your g of s h of s. Why? Because h of s is 1. Okay, so this is your open loop transfer function. Now we have already studied, so based on the I mean, if you have any doubts you may check that. That is the type of the system and the steady state error. So this is a type 1 system, right? This is a type 1 system. Okay, and the static error coefficient that we defined for a type 1 system is the velocity error coefficient. Okay, velocity error coefficient k suffix v. Okay, hope you might be remembering. If you have doubts, you may just refer my previous videos. Okay, so, and how we have defined there, so we have defined that kv as, okay, kv is defined as limit s tends to 0 s into g of s h of s. Okay, g of s h of s, or h of s is 1 over here. So you can write like this, k limit s tends to 0. So what is your g of s h of s? It is equal to k into kc by s into s plus a, or when you put s is equal to 0, okay, when you put s is equal to, so you can substitute this s into, this is s into s, this s and s will get cancelled. After substitution you can see that this will be k into kc divided by a, right? Okay, so where k into kc by a. Okay, so that is your kv, right? Okay, so how will you find out the steady state error? So now we know that the steady state error, okay, if you have doubts you may look into the previous video, due to the ramp input. Okay, ramp input in terms of this kV, or the velocity static error coefficient, is given by ESS is equal to, this we have already derived. Okay, this is very important, you must learn it. So this is 1 by kV. Okay, so if it is equal to 1 by kV, then that's going to be, we have already derived the value of kV to be k into kc by a. So your steady state error will be a by k into kc, right? K suffix c. So what do you infer from this? That is a steady state error due to the input. So if the ramp is the input that you provide to the system, then the steady state error, okay, decreases as you increase your kc. That's what this suggests. So once the plant is fixed, this is a fixed, you cannot change it. The only thing that can be changed is kc, and this equation also shows that the steady state error due to the ramp input also shows that as you increase the proportional controller gain, okay, the proportional controller gain, you can steady state error gets reduced. Okay, so we got the two important inferences. So the inference here also is the steady state error due to ramp input decreases as kc is increased. Okay, so in both the cases we have seen that, in both the cases, for the disturbance also as well as for the input, if you can increase this gain, now the steady state drastically reduces. Okay, that's a very good point, and that's a very advantage. That's one of the advantages of this proportional controller. But now the question is there any limit for this gain? Can you increase this gain indefinitely or as you like? That's the next point which is to be cleared. Okay, so for that let us consider the characteristic equation. What is the characteristic equation? That is 1 plus gs hs is equal to 0, right? And what is GSHS? GSHS is k into kc by s into s plus a, right? K into kc by, so rewrite, so you can you will get the characteristic equation as k into kc divided by s into s plus a is equal to 0. Okay, so now you can have the manipulation of this, so you can bring over here. So this will be s into s plus a plus k into kc is equal to 0, or this is equal to s square plus as plus k into kc is equal to 0, right? Okay, so this is equivalent to, this is actually the characteristic equation of a second order. This is a second order system because it's having a highest order. So if you can write the general characteristic equation of a second order system, that is given by s square plus 2 zeta omega ns plus omega n square is equal to 0. Okay, so this is the general second order system you have already studied in second module. Now comparing these two equations, I call this as equation 2 and this as equation 2 and this as equation 1. Comparing 1 and 2, you'll get omega n to be equal to, or omega n square is equal to k times kc, or omega n is equal to root of k into kc. Now there is an important information that you will get from this. What is this omega n? Omega n refers to the natural frequency of oscillation. Okay, so what is the meaning of high omega n? Omega n increases means oscillation increases. That is, the output starts to oscillate at a particular natural frequency. So the impact of this is, the impact of the natural frequency of oscillation gets increased as Kc is increased. Now, what we have learned here is, so in order to reduce the steady state error, which is a much needed aspect in a control system, the purpose of a control system itself is to reduce that error. Now, the steady state error can be for in both the cases, that is from in the perspective of disturbance as well as in the perspective of the input. We have seen that the steady state error can be decreased by having a high value of Kc. Okay, now this particular aspect puts a limit for increasing increasing the gain of the proportional controller, because as you increase, this equation suggests that the natural frequency of oscillation increases, or it can drift the system to instability. Okay, so that is the problem with this proportional controller. So what is an advantage of a proportional controller? Now, in a proportional controller, you can reduce the steady state error by increasing the proportional controller gain. But the problem is, as you increase, another important aspect gets affected, that is the stability of the system, or the system tends to oscillate because of this, and this can be explained by this equation. Hope it is clear. So that is all about proportional controller. Okay, now let me list out the features or the effect of proportional controller. Number one, increasing the value of Kc reduces the steady state error. Okay, that's the number one point. Now, second point is high value of Kc tends the system to instability, right? Or tends the system to be more oscillatory, or effect, and the consequence of this is it is again due to the high Kc that will make the system unstable, or it drifts it to instability. And when the error is zero, the output remains at a constant value. Okay, constant value, and that all depends on the final value of that error, and all such things. Okay, anyway, these are the important points that is to be noted under the proportional controller. So now we are going to, next is the derivative control, that is next. Okay, now the next is the derivative controller. Now in a derivative controller, the output, right? So the output, or the controller output, EC of t, will be proportional to the derivative of what? Derivative of the EA of t. Okay, you must not forget what is this EA of t. So that is, we have started from the basic block diagram as EC of t is the controller output, EA of t is the actuating signal. So the controller now this controller will be giving an output not proportional to E of t, but it is proportional to the derivative of this, derivative of EA of t. Or now you can have it can be equated with the constant of proportionality, and I'm calling that as Kd. So in the previous case, I have called that as Kc, while in this case, you are calling this as Kd into EA of t, that is EC of t. Okay. Now we are interested only in the S domain. When you convert this into S domain, that is EC of S is equal to K suffix d into what? It is d by dt, right? Into the Laplace transform of Ea of t. If you assume the Laplace transform of Ea of t as Ea of s, what is the Laplace transform of the derivative of this function? D by dt of Ea of t will be s into Ea of s minus Ea of 0, right? But here the initial condition, we assume the system to be a relaxed system, so the initial condition is equal to 0. That means you can find out the Laplace transform of this as s into Ea of s. Okay, now the block diagram, now look at this. Now you can see the block diagram of a controller. This is just a part of a control system. Okay, we are not least bothered about the other parts. So the block of a controller is given by, so you have an actuating input Ea of s, and that Ea of s gets multiplied by the term Kd into s. So s into Kd forms the S into Kd, or rather this S into Kd represents the derivative gain, or this Kd is what is called as the derivative gain. This is the derivative gain, or it is also called as rate gain. Okay, now why it is called as a rate gain? Because this is proportional to what? The controlled output is proportional to the derivative of the input, or in a sense you can say that this is proportional to the rate of change of input. Rate of change of input, right? Okay, so when you draw the block diagram, don't forget to put this S into Kd refers to the Laplace transform of this derivative of this function. Okay, so this is the block diagram representation of a derivative controller. Now the next is, let us see the effect of a derivative controller. What is the effect of this derivative controller? For that, we are considering a case. So consider the block diagram as shown in the figure. Okay, now this block diagram actually shows what? This block diagram actually shows the control due to the derivative controller. So you have a KDS block, KD into S block, which represents the transfer function of the derivative controller. Okay, and this actually the representation of the transfer function of a process. Okay, so there we have considered a different process, K by S into S plus A. Here you are considering again now in both the cases they are second order system. So this is also a second order system. So you have this is K by S into S plus A into S plus B, which represents the process. This is the process to be controlled, and this is the derivative controller. Okay, now before going into the analysis, I would like to say something about this. Now look at this. When what happens when the actuating signal is a constant? Now when this E A of t is constant, okay, suppose this E A of t is a constant and the controller that you use is a derivative controller, what is the output? The output is going to be Kd into the derivative of a constant, which is going to be equal to 0. Okay, so the derivative controller will not produce any output if the actuating signal is a constant. Okay, that's the number one point. If the actuating signal is a constant, then the derivative controller will not produce any output. Do you know the reason? The reason is Ez of t is equal to Kd into the derivative d by dt Ea of t. If the actuating signal, or Ea of t, it is a constant, so the derivative of a constant which is equal to 0. So Ez of t will not be producing any. So what happens at the steady state error? So this in the steady state error, the steady state once it reaches the steady state, Ea of t won't be changing. See, once a system reaches the steady state, for example, once it reaches the steady state, what is the meaning of steady state? Now no longer the error is going to change. So the error is going to be a constant. That is, the actuating signal is going to be constant. That is, the steady state error will not be, steady state error remains uncontrolled in the in the derivative control. Okay, it remains derivative under the derivative control, because derivative control always comes into play if there is a change. Okay, or in other words, it always checks the rate of change. If there is no change, then the controller produces no output. So what I want to convey is this derivative controller. So you know that for a second order system, for a step input, you have studied something like this. See, like, okay, so this we call as the transient response. So what is the specialty of the transient response? During the transient response, this keeps on changing. That is, the EA of t, or the actuating signal, keeps on changing, and till it reaches a steady state. Once it reaches the steady state, it almost remains a constant. So the derivative control has got least importance once it reaches the steady state. So it will be having an importance during the transient state. Okay, so derivative controller is controller action is effective. This is a very important point. Effective only in the transient period. Only in the transient period. Hope you understood why it is so. Because in the transient period only this changes, and derivative controller is more effective when you deal with the changing or varying input. Okay, right. Okay, so that is why it is called as a called as the rate controller. So because of this nature, because it is more effective in the transient state, this won't allow the system to go this won't allow the error to go more, okay, to becoming this prevents the error to become too large. Okay, so that is the meaning of this derivative. That's the importance of this derivative controller. Okay, right. And let us see some more effects using this this block diagram. So you are considering a case using this. Let us see some more effects of the derivative. These are the primary things which I have told about the derivative controller. So the primary thing, the most important aspect we discussed is this is effective only if the input varies. So that means in the steady state error, this has got least effect. So this is more in the transient state. So let us see the impact of this derivative on this transient state. Okay, now let us see to study the effect of this derivative controller on this control system. Let us see the case. So first of all, let us try to write the characteristic equation without derivative control. Okay, that means you are taking off this. Okay, assume that you have only this, that is your function without any sort of control. So if that is the case, then your g of s will become k by s into s plus a into, so your g of s now will be equal to k by s plus a into s plus b. So from this you can find out the characteristic equation without the derivative control, that is 1 plus gs hs equal to 0, or that is equal to s square. So you can do that. So instead of GSHS, you may substitute k by s plus a, and you may do it by yourself, so that you will get this as s square plus a plus b into s plus ab plus k, where k is the forward path gain of this. Okay, this is equal to 0. So this is actually your your characteristic equation. Now this can be compared with the general characteristic equation of a second order system. So from this you'll be able to get omega n. Comparing these two, this is equal to 0. Comparing these two equation, you will be able to get omega n to be equal to root of ab plus k, because this part represents what? This part represents omega n square. So this is ab plus, okay, this will be root of a into b plus k. Okay, so ab plus k. And the damping ratio, how will you find out the damping ratio? Now from this you can see that when you compare these two, you will be able to get 2 zeta omega n is equal to a plus b or theta is equal to, so what you will get as theta. So from this you will get theta as a plus b by 2 omega n, a plus b, okay, this is a plus b by 2 omega n, a plus b by 2 omega n. We have already derived the omega n to be ab plus root of ab plus k. So this is your theta, okay, ab plus k, right? Okay, so this is your theta. So this is omega n and theta without feedback. Without the derivative control. Without the derivative control. Now let us see what is the impact when you add this derivative control to this block. Okay. Okay. Now let us see what is going to be the characteristic equation with the derivative control. Okay, with the derivative control. So once when you attach this derivative controller here, your g of s becomes this product of this and this. So that will be, so your g of s becomes equal to k into, okay, kd into s divided by s plus a into s plus b. Okay, now you can find out your characteristic equation 1 plus gs hs equal to 0 using this gs. Now what is your hs? Hs, as always, it is equal to feedback, unity, right? Hs is equal to unity. This is a unity feedback system. So you can find out 1 plus gs hs is to be equal to, so you may do it by yourself, so that you will get this expression as s square plus, okay, s square plus a plus b plus k into kd into s plus ab is equal to 0, right? Now from this you can find out the damping ratio. Now how will you find out the damping ratio? So from this you can find out omega n square. So this is equivalent to s square plus 2 theta omega ns, okay, omega ns plus omega n square. So from this you will be getting your omega n square as, okay, your omega n square will be equal to ab, or omega n is equal to root of ab, and from this side to theta omega ns, so your 2 theta omega n is equal to a plus b plus k into kd, or your theta will be equal to a plus b plus k into kd divided by 2 omega n. And what is your omega n? Omega n is equal to 2 root ab, right? So this is your zeta. So this is your theta with derivative control, while this is your theta without derivative control. Okay, now let us compare these two equations. That is, let us call this equation as, say, as 2 and this as 1. Okay, comparing these two equations, what you will get this as, you can see that the impact of k is nullified in this. So what happens when the denominator reduces? So what you can see is the denominator gets reduced while the numerator gets increased. That means your theta value, that is the damping ratio is improved, right? Is improved or increased. Now what is the meaning of damping? Damping means if there is any sort of oscillation or if the system tends to oscillate like this particular system offers a damping so that it reduces the oscillation. So this is an advantage as far as a control system is concerned, because a control system, because of any external disturbance, that system can tend to oscillate or tend to instability. So this will be prevented by this derivative controller. By the introduction of derivative controller, what we have seen is the theta or the damping ratio gets improved. That means, say, when you compare these two, right, the k gets reduced, that is the denominator gets reduced while the numerator gets increased by a factor K into KD. That is the gain of this process, as well as the product of gain and the derivative control gain. So that much it has been increased. Okay, so the theta value gets so the okay, right. So that means this, what is the impact of this? Because of the high damping ratio, this will always makes the I mean, if there is a tendency of increasing oscillation, that will get reduced. So it will see that the system will never try to oscillate. Okay, right. So that is the impact of this, or it improves, in a sense it improves. Okay, that the theta value gets improved, and that is a great advantage as far as a controller system is concerned. Now, okay, now in the consequence of this damping ratio, the improval of damping ratio is going to affect the three parameters which we have already studied for a second order system subjected to a unit step. We have seen these three, that is the maximum overshoot, settling time, and rise time. When you look at this expression, this is e raised to minus pi into theta. Do remember, we have derived this expression under the assumption that 0 theta lies in between 1. So as the theta gets improved, what happens is, since it is less than 1, theta square is anyway, as it moves greater, the theta square becomes less. So the impact is very less over here. So we can see the denominator factor is increased, right? So increase means the exponential of the negative is increased, right? That means 1 by e is increased, or in an effect 1 by e gets reduced, right? Since this parameter, since theta increases because of this negative sign, this mp, that what is going to be the effect of mp? The effect of mp is it gets reduced, right? Since it is more high, so the mp, or the maximum overshoot, the meaning is, say suppose you have a control like this, a control like this, right? I mean, a system like this whose output response is this. If you connect a derivative control, this maximum overshoot reduces. That's the meaning. This maximum overshoot reduces. That's a number one, and that is an advantage. So anyway, it should not, the peak overshoot has to be limited. Otherwise, that can damage the system if it would be very higher than the designed value. Okay, it should not go beyond a designed value. So maximum overshoot has to be limited. So that is one of the advantage, and that is a consequence of increasing damping ratio. Now look at the settling time. What happens to the settling time? What is settling time? Settling time is actually the time the system takes to reach the steady state. Okay, now as theta is increased, what happens to ts? Ts decreases. So this system becomes faster. That is another advantage. So because of the presence of this this derivative controller, the system gets faster. And what about tr? We know that tr is given by pi minus phi by this thing, right? Okay, what is phi? Phi is equal to I mean, theta is equal to cos phi, or from this you will get this as cos inverse theta. Now as theta increases, what happens to cos inverse? Cos inverse reduces, or effectively tr increases, right? Okay, that's a that is a drawback, right? So the rise time increases. Rise time increases means it will take some, it will be sluggish during the initial period to reach. That is the rise time. How will you define the rise time? It is, for an undamped system, it is the time taken to reach the 100% of the output. So this is the time. So this time will be sluggish, or this is sluggish. This is the system will be, the derivative controller is sluggish initially, and what happens is after this point, this increases and but reaches the steady state very fast. Okay, so that is what this shows. Okay, so we have seen the greatest impact of the derivative control is its impact on the damping ratio. The damping ratio gets improved. On consequence of that, the maximum overshoot and settling time gets increased, and the drawback of that is rise time is increased. So rise time is increased means it will be sluggish initially, okay, or it will be lazy initially, right? Okay, to summarize, this is the advantage. It improves the damping ratio, so consequently, the maximum offshoot reduced, the settling time reduces, which and the consequence of this is the fifth advantage or the fifth point. Since the settling time gets reduced, controller response becomes fast, but initially it is sluggish. That is the reason, and because of that, this TR gets increased due to the consequence of theta. Okay, hope things are clear. So these are the some of the advantages and drawbacks of this. So in comparison to this, even though I haven't mentioned in the proportional controller, so you will be getting one of the drawbacks in the proportional control. One is it can go to instability, another with the point regard to this speed. Okay, so anyway, derivative controller is faster than the proportional controller, so you can right. So in this you can also add one more drawback of this. What is that? The response is slower in comparison to what? In comparison to derivative controller. Okay, so as we study different types of controllers, you can add these advantages. By comparison, we can add some more points to all these things. Okay, right?